Welcome to our Nature Nanotechnology 15 years anniversary webinar. Today it's our honor to have Professor Rich Masel from Dioxide Materials and Professor Yi Cui from Stanford University. We will first start with Rich Masel. Rich retired from IUC in 2010. He is a very successful electrochemist and very experienced entrepreneur. He is currently CEO of his third startup company, Dioxide Materials, founded in 2009, which is developing processes for carbon dioxide conversion to fuels and chemicals as an economic way to reduce greenhouse gas emissions. Prior to founding Dioxide Materials, he helped found Tycoon, a developer of fuel cells for portable electronics, and Chabana Laboratory, which develops homeland security products. Both are now independent companies with professional management. Now let's start with Rich Masel's talk, Converting CO2 to Useful Chemicals via Electrolysis. This talk was recorded, and Rich is here. He will join us in the Q&A session. Fabio, can you please start?
Hi, I'm Rich Masel from Dioxide Materials, and today I want to tell you how carbon dioxide can be used as a feedstock for the chemical industry. Before I start, I want to thank the Nature team for inviting me and thank my co-workers, Zheng-Kai Liu, Hengjiao Yang, Eric White, and Mike Resch for taking all of the data in this presentation.
One might ask why CO2 electrolysis belongs in a symposium on nanotechnology. CO2 electrolysis would never be commercial without major advances in nanotechnology. When I started in 2009, there were two kinds of catalysts available, pure metal catalysts and organometallic compounds. Pure metal nanoparticles never showed the activity and selectivity needed when needed to go to a high voltage, and a lot of side products were formed. Organometallic compounds had ligands that allowed one to tune the selectivity, but the rate was limited, and they only lasted for about 1,000 turnovers, when needs hundreds of millions of turnovers to be practical. A key advance happened in 2011 when a new type of catalyst arose, metal particles surrounded by ligands like those in the organometallic compounds. The metal particles had a high enough electron density to enable high rates of electron transfer. The ligands allowed one to tune the properties of the surface layer to improve rates and block side reactions. People worked to optimize ligands for about 5 years, but there was still a problem with ligands, in that the ligands were removed from the metal particles after hundreds of hours on stream. That's not good enough commercially. So people switched to polymers containing the ligands. We, for example, use a polymer containing imidazolium ligands, and that allowed us to get the long lifetime. At this point, people don't talk about ligands anymore. Instead, the people talk about metals coated with polymer ionomers, but the idea is the same. You need metal nanoparticles with the critical ligands to get good performance.
When I was preparing the talk, I had to decide whether to make the talk a specialist talk or a generalist talk. And I decided to do a generalist talk. So I'm not going to concentrate on the details of the science here. Instead, I want to give you an overall picture of the field, starting with why people are interested in using CO2 as a feedstock for the chemical industry, tell you how an electrolyzer works, briefly mentioning the early work that led to the development of the hybrid catalyst, and then give a synopsis of where the field is. And of course, I will mention my company. Next, I want to talk about why there is interest in using CO2 as a feedstock for the chemical industry. We all know that CO2 regulations are coming. Chemical petroleum companies are large emitters of CO2, so they're going to be under increasing pressure to do something about their emissions. And they're not very popular with the environmentalists. So many chemical companies have promised to achieve net zero carbon emissions by 2040. Well, that's really hard. You've got to do something more than just make the system more efficient to get to that kind of a rate. Now, to really reach net zero, you're probably going to have to look at alternative feedstocks that do not depend on fossil fuels. Right now, there's a natural gas shortage, which is affecting chemical operations in some countries. Also, it's not clear that chemical companies will be able to get to net zero as required if they don't switch to a feedstock that doesn't involve fossil fuels. And you have to remember that chemical companies have a large investment in existing equipment. It takes a very long time and a lot of money, billions of dollars, to build a new chemical plant. And if you have to start over, get the environmental regulations, it's just a very hard thing to do. So what most companies would like to do is to do retrofits to make their plants work, rather than having to build an entirely new plant. So how can a chemical company move to net zero emissions? Obviously, one way is to develop new processes. If you want to start over from the ground up and build a new process, then you can build processes that produce less CO2. But that's really expensive. And people can't, it's going to require years of work, and many processes will not be able to economically be viable in these new things. So if electrification doesn't work, there are a couple other alternatives. Another alternative is to bury the CO2. The Department of Energy has been spending billions of dollars to try to get this to work. There is actually one plant where they tried it, but the plant ended up shutting down because they could never get it to work effectively. And if you can bury the CO2, you can get rid of the CO2. Now, to do that, you've got to deal with a lot of NIMBY suits where people don't want it in the backyard. And you also have to worry about the liability if it ever leaks. If the CO2 leaks, your company's bankrupt. So this is something that people are talking about and could work, but has a lot of risks in it. The alternative is to pay someone to haul the CO2 away. Shell's building such a thing in Canada. And if you can do that, that is a viable alternative to cut your CO2 emissions. The best alternative is just to convert the CO2 into something you can use yourself. If we can take the CO2 and use it directly in my process and never have to bury it, I no longer have to worry about the liability. I don't have to worry so much about just restarting over a new plant. I don't have to worry about all the things that happen by putting something underground. Instead, I can just use this stuff right in my plant, and then I'm all ahead because I actually make money at it. Well, Oxide Materials' idea is to convert the CO2 into feedstock for the chemical industry. The advantage is the first thing, it lowers the CO2 emissions. People obviously want to get the CO2 emissions down, and that's one of the ways to do it. But you can't get to net zero emissions by still using fossil fuels as your feedstock. And so to get to net zero, you also have to use a different feedstock, and the feedstock could be CO2 from either air capture or from some biological source. And then that would let the companies get to where they need to be. The other part of this is that this is conventional chemical engineering. People can design these systems. Electrolyzers are just separators and reactor separators, and it's just standard chemical engineering. You don't need to know omics. It is just things that all chemical engineers know how to do. All the companies have the expertise already. You don't need to develop whole new expertise to do this kind of work. Why not use biology to create all your chemical products? You would have thought that if you build a biorefinery, you'd eliminate all your CO2 problems. But actually, you don't. If you look at an ethanol biorefinery, half of the carbon in the sugar gets into products, but the other half is emitted as CO2. So, in fact, if you have a biorefinery, you still have a CO2 problem because half of your feedstock is ending up in CO2. If you look at most biorefineries, they produce more CO2 per pound of product than most chemical plants. So biorefineries alone can't meet your needs for net zero carbon because they're major emitters of CO2 themselves. Our approach is to use an electrolyzer to convert the CO2 and water into chemical feedstocks. An electrolyzer is just a machine that takes in CO2, water, and electricity and makes feedstocks for the chemical industry. We've been making carbon monoxide, formic acid, hydrogen, some ethylene. Other people are making ethanol and oxalic acid, and you can do this very easily. Now, to make this green, you've got to use renewable energy or nuclear energy to get the thing to work. But of course, if you don't, even if you use conventional energy, it still works. You just have to depend on the utility to take care of the CO2 that's produced. And once you have CO, hydrogen, and formic acid, you can make all the products made by the chemical industry. You know, there's the old Fischer-Tropsch process where you can convert CO and hydrogen into gasoline or into any hydrocarbons you want. We looked at formic acid, a different product. You can make that into formaldehyde. We've done that. That means you can make an isoprene rubber, which is using styrene isoprene. You can make spandex out of that, make a whole bunch of solvents out of that. We've also made acrylic acid from formaldehyde, and then that's all the acrylates that you talk about, you know, out of it. So there's a whole wealth of stuff you can make if you start with CO, hydrogen, and formic acid. And then, of course, people can also make ethanol and ethylene, and that gives you a wide range of products that you can actually manufacture. Next, I want to talk about how does an electrolyzer work. Here's a cross-sectional diagram of an electrolyzer. Now, what an electrolyzer is for the engineers in the audience is something that combines a standard chemical reactor and a membrane separator into a single device. Now, this is, I've taken the example of CO2 being converted into CO and oxygen. And what you do is you feed CO2 with a little bit of water into the cathode of an electrolyzer. It goes down all these little flow channels and out again. And the CO2 reacts to form CO and oxygen. That's a good reaction. But the magic is that this also does a separation. So most of the oxygen leaves on the anode side, and most of the carbon monoxide leaves on the cathode side. So we've done both a reaction, like you would do normally, but also a separation, and that products come out two different streams. Here are some of the details. Actual reaction occurs on something called a membrane electrode assembly. And the membrane electrode assembly includes an anode electrode, which has catalyst in it, a membrane to do the separation, and a cathode electrode with catalyst in it that also does some reactions. Now, when I attach this to a battery, what happens is electrons flow from the battery and into the cathode. When the electrons flow in the cathode, the electrons can react with CO2 and water and form my carbon monoxide that I want. It can flow out of the system, and it forms hydroxyls. And hydroxyls are, of course, soluble in water. There's a lot of water around this system. And so what happens is I've got these hydroxyls, and I had not formed any oxygen on this side of the membrane. If I continue, what happens is the hydroxyls go across the membrane, and there they react to form water, and the oxygen forms on the other side of the membrane and gives me the two electrons I need, which can flow back through the battery into the cathode. Now, what's magic about this is that the CO is formed on one side of the membrane, and the oxygen is formed on the other side of the membrane, and there's a lot of water in the membrane. So what happens is, you know, CO and oxygen aren't very soluble in water. It's actually it's an alkaline solution, aren't very soluble in water, and so the oxygen mostly flows out here. It doesn't really transfer through the membrane unless you have a hole in it. CO forms on this side. It doesn't really flow through the membrane on the other side, And so you get a pretty good separation between the oxygen and the CO. CO2 is different because CO2 can react with some of the hydroxyls and can be carried to the other side. So you do get some CO2 into the other side of the membrane. Well, why wasn't this done years ago? And basically, if you look back to the previous slide, you'll see that what we need is we need good catalysts and good membranes. And at the time we were starting this in 2010, we didn't have good membranes and we didn't have good catalysts. So if we had a catalyst here, what would happen is you would try to make CO2 and try to get to CO, and it wasn't very much change in free energy, but you'd have to form this intermediate that was very high energy. And so you're wasting a whole bunch of energy. And not only that, but you're also producing hydrogen because you put so much extra energy in this thing, the electrons, it's much easier to form hydrogen than it is to form CO. So your selectivity was low and your activity was low. The other thing we needed is alkaline stable membranes. The membrane had to be alkaline, which is a basic membrane, rather than acidic membranes. The problem with acidic membranes is if you have an acidic membrane, then there's many more protons than there are carbon dioxide. If you have an acidic solution, carbon dioxide is not very soluble in it, but protons are very soluble. There's lots of protons around. And so you mostly formed hydrogen. So you needed to have something that was alkaline to make sure you don't form so much hydrogen and to allow CO2 to be easily absorbed. So the first thing that happened is that we wanted to see, this is my old work, we wanted to see what we needed to do to get this thing to work. And the first thing we discovered is that you had to have nanoparticles. People had done this with bulk crystals. They had some particles that were big. A lot of people were doing sort of these single atom clusters with all kinds of ligands, and neither of those worked very well. What you had to have is a metal cluster compound, metal cluster that had enough electron density of states to actually easily transfer electrons to the system. And so there was a critical particle size. So if you were down below 1 nanometer, you didn't get very many electrons going to CO. And if you were kind of out to the bulk, you weren't. But in this intermediate particle size, everything worked very well. And what was special, what was weird about this, of course, happens to be the particle size that Sigma Aldrich and Alpha Acer sell all the time. So the particles that you can buy the easiest happen to be the most active. But that wasn't good enough because we still got too high of an energy barrier and too high of and not good enough selectivity. You still produced a lot of hydrogen.
Now, in order to get the rate and selectivity you need, we need to make an additional change. And the additional change was to add ligands to the surface of the catalyst. You look on the right, what we were doing is adding imidazolium ligands to the surface of our silver or gold. And so what that did is it produced a positive charge on the surface that eliminated the hydrogen. It repelled all the protons. And so what happened is we got much higher selectivity. But much higher selectivity wasn't enough. The ligands that happened that the ligands also helped us create a low barrier to reaction. Remember last time we said that we were going over the black line, which formed this high energy intermediate. But when we had a imidazolium in there, we could go over the green line instead. In this case, there was a complex formed between the CO2 and the imidazolium, so like a Zwitterion kind of thing, and we would have a much lower barrier to reaction. So what we found is that by coating the surface with these ligands, we're able to both improve the selectivity and reduce the barrier. Well, that's of course the same thing you see with ligands in organometallic compounds. We just did the same chemistry that everybody had been doing before, but we did it in a new system where we use metal particles, rather than using small metal clusters. And that meant we could use 40% less energy. Here's the kind of thing you see. Say we want to run a stack to produce
20 kilograms an hour of carbon dioxide. If Siemens had done this before us, they found they needed 200 kilowatts of power to run this thing. But when you did it when you added the ligands to the surface, suddenly the amount of energy went down to 220 kilowatts. So you saved 80 kilowatts, 40% of the energy, by adding the ligands to the surface. Now, the other thing I said before is we needed membranes, that were alkaline or somehow make everything alkaline. And what a lot of people did is they just fed carbon. They started with an acidic membrane and just fed potassium hydroxide into the system, and that works, and you get good performance. But the problem is it's not industrial. That is, if you have CO2 and potassium hydroxide, you form all kinds of carbonates. They clot up everything, and eventually you end up with something that's not very useful. So what we also did is said, well, you have to use an anion exchange membrane. Now the problem is that at the time we started this, there were no anion exchange membranes that were stable. For example, this is just running. It happened to be in water electrolyzer, 1 mole is 60 degrees C, and we tried a whole bunch of membranes. Here's the best of the commercial membranes, which is a Formic FAS50, and it lasted about 200 hours in the cell before it just completely fell to pieces. And then, of course, that's not acceptable industrially. And so we had to work on another membrane, and we have found some that lasts thousands of hours. This is a 10,000-hour run in these kinds of systems. Now think about this. We're talking about 1 mole of KOH at 60 degrees. So that's basically Drano at high temperature, at hot water, and we put it in there. You know what Drano does? You just put it in at room temperature. It eats up all the clogs you have in your drain. Think about what would happen if you did that for 10,000 hours. We ran it. The longest we've run is about 12,000 hours, so 18 months. Think about what would happen if you continuously fed Drano and hot water into your pipes at 18 months. You think you'd have any pipes left? Well, somehow, magically, this did happen, and we were able to run for a long time.
Once industrial rates were demonstrated, the field grew tremendously. We had only 45 papers on CO2 electrocatalyst in 2012, and there was over 600 in 2021. And a whole bunch of companies are working in the space.
Next, I want to talk about where the field is today. Now, there's a lot of work today. I mean, there was 600 papers last year, and obviously I can't talk about all of those, but what I want to do is just give you an idea of sort of the very high level things that are happening in the field to understand where we are and where it's going. So first thing, what products are people looking at? The two products that I like, which are carbon monoxide and formic acid. Both we, 12, and Siemens are working on carbon monoxide. In this case, for reaction, we react CO2 and water and 2 electrons. I showed this reaction before to form carbon monoxide. And that, I call it pre-pilot. There's multiple kilowatt units out there that several people are running now, and we can try to do it. These haven't done real pilot plants with an industrial feed and an industrial application, but these are close to pilot devices. Formic acid also, it's a little smaller here. These are probably less than a kilowatt of most of the ones that are out there. There's one run that DMV did that was a little larger than that, but it was they didn't make formic acid, they made calcium formate, and it was run what I'll call a little smaller scale, but we call this bench scale in the things. And both of these are moving, have a relatively straightforward route to commercialization. Ethylene and ethanol are a little behind that, in my opinion, You can make ethylene at high conversion and a mixture of ethylene and ethanol with high conversion. The problem is the ethanol goes through the membrane and is oxidized, so you lose ethylene. The other thing is that people are running this mostly in potassium hydroxide, and that works perfectly fine if you're doing a lab scale device. But when you're actually running in the field, the problem is you have calcium hydroxide or potassium hydroxide and CO2, and you feel carbonates, and the carbonates precipitate all over the place, and you have a problem with that. There's been a lot of work on oxalate at a company called Liquid Light that's no longer in business. In their case, this was what looked like a very interesting reaction because it was only a one electron reaction, and it was actually slightly endothermic. But what happened is you had to run this in a non-aqueous electrolyzer, and that's just very hard technology to get going. Membranes don't survive, the system doesn't survive, and they were never able to get anything that really looked like it was commercially viable. There's also been work on methane and propanol. Methane has been talked a lot. It just is very expensive to make this way because it's an 8-electron process. And propanol, you can do it in principle, but usually propanol ends up to be, you get a mixture of ethane, ethanol, and propanol, and it's just usually just a side product of the reaction. So let me talk about carbon monoxide first, because CO2 conversion to carbon monoxide is the one that I judge to be closest to commercialization. So again, here's my cell in this system. Again, what you have is just a MEA. You feed in CO2, get out CO in one stream and oxygen in another, and you have to deal with that kind of thing. So a little bit about the catalysts here. The thing about this is that you have to talk about what happens on the cathode and what you hook on the anode. And if you look in the literature, there's hundreds of papers that have looked at all this stuff. But really only two of the real cathode catalysts have really survived and being able to show long-term performance and high selectivity. One was silver with the imidazolium ligands that I talked about that. The other is gold with some amine ligands that don't tell us what it is. And both of these show long-term stability and reasonably high selectivity. Now, in silver, people have tried instead of using the standard nanoparticles, all kinds of other structures, porous structures in single atoms, smaller atoms, all kinds of interesting shapes. Nothing showed activity that was any better than the stuff you could buy from Alpha Acer or US Nano. You just buy the standard stuff and it works better than everything else. Gold, there is more of a not a consensus there. Some gold people have found that gold that you can. Part of the problem is that you can't buy gold that has the right particle size. At least we've not been able to find it. And so there is some work to do. You also need to work on the ligands. 12 is using some amines that don't tell us about, but there is that. And so there's more work to do on gold. The big thing with gold is so far the selectivity has been lower than the silver with the imidazolium ligands. And I don't know if that's just because they didn't use the right ligands or they didn't do the right things. Now, you can get carbon monoxide production on copper alloys, but you get a lot of hydrogen. There's been lots of work on single atom catalyst and potassium hydroxide. Again, potassium hydroxide is not something you really want to do industrially, but you can run it, and the question is how long does it last? And nobody's done the thousands of hours. On the anode, right now, most people use iridium-based anodes, usually iridium oxide nanoparticles or iridium-based mixed metal oxides. And iridium has gotten very expensive recently. It's used to make crucibles that they use to make parts for 5G cell phones, and so you're competing with cell phones for the limited amount of iridium that's made every year. And the result in that is that iridium has gotten very expensive. And so there is a real need to do something about it. People have tried different things like ruthenium-based catalysts, and tried to do that. So far, it hasn't shown the activity and stability you want. If you're running KOH in the system, you can run nickel iron moly in the system. We've done that. It works perfectly fine. Stainless steel works perfectly fine, but it only works if you have your pH is above 12, which means basically, 13 pH means you're basically having dilute KOH, which means that you can't maintain that while you're feeding CO2 into the system unless you just keep adding new KOH each time you do it. But the good advantage of carbon dioxide is it showed very good selectivity and long-term stability. Here's some of our data. We ran this for 3,500 hours. We've run longer runs than this, but lower currents. This, I guess, was around 200 milliamps per square centimeter. And usually how these fail, as now you can see, is not something that happens in the MEA and the electrolyzer, but it's usually something that happens like a pump dies or something like that. And in this case, what happened is during a hurricane, the power supply blew up and did the cell. But that's the kind of thing that you can see. You can run these for thousands of hours with basically no loss in performance. And the currents are reasonable. This is some of our data. We've run up to 600 milliamps per square centimeter at steady state. And you get reasonable voltages and you get reasonable things. And so this is talking about, yet you can get reasonable voltages, but you have to go to 3 volts basically to get there. People would like to run at 2.5 volts, but you can see this is only 50 milliamps per square centimeter here. We've done a little better than that, but that's when you're talking about having to use iridium and 50 milliamps per square centimeter, that gets to be too expensive. And so there is a real need to get the voltage just a little lower, but without having and get rid of iridium, but without having to do it. Now, one of the things that's important for an industrial guy like me is can this run in a real stream, not just the pure CO stream. And this is a simulation we did where we took all the impurities that are typically in a output of an ethanol fermenter, and we did that, and we tested it and stacked voltage current. And you can see when you turn it on and change to impurities, we can't see any change that happened according to that. This is a 3-fail stack, by the way. It just was flat. Where impurities don't do it. Now, I should point out that this only had 190 ppm of oxygen. That was important for all this thing. We've done SOx NOx. That also doesn't have any real effect until you get up to hundreds of parts per million, and no real plant has that kind of thing. Now, we do see degradation with H2S. Now, a ethanol fermenter, the output only has about 1 part per million of H2S. And at that point, it doesn't affect it. There's an equilibrium between absorption of H2S and removal into the solution. And the equilibrium is such that H2S up until 3 parts per million doesn't do anything, but then you start to accumulate sulfur on the surface and you start to see some poisoning. But again, there's no real industrial application of that, right? Nobody uses that much sulfur. If you do, you use a sulfur trap. The one thing that was really bad is oxygen. We've been running on flue gas, and when you run, I'll show some data on this in formic acid later. And what happens is you're feeding a mixture, say, that has 10% oxygen and 10% CO2 into the electrolyzer, and you make carbon monoxide or you make formic acid. Well, carbon monoxide is flammable, and you have oxygen, and you've got carbon monoxide, which is a fuel. And what happens is you can get a catalyst, so you can get heat. So what actually happens is you're running this thing, and then you get a hot spot, and it uses up everything, and then it cools down again, and you get a hot spot. And not only that, but if you produce a mixture that has as much oxygen as carbon monoxide downstream, that's an explosion hazard. And so we need to be real careful with oxygen. We found that all the things you would have expected, the catalyst guy would have worried about SOx and NOx and low concentrations of sulfur compounds, does nothing. But when you get to these high concentrations of oxygen, which you can get, that's really bad because the mixture you get is pretty dangerous, and we have to avoid it. So that basically means that when you're doing these kinds of things, you have to remove oxygen before you make something that's flammable, or else you're in trouble. Now, present issues, the stability needs improvement. We've ran it for about 4,000 hours, no real degradation. But to be commercial, I need to get to 24,000 hours. And the problem is at 4,000 hours, you see nothing, right? The only time it fails is either there's a hole in the membrane, which could happen some of the time, or something happens in one of the peripherals. I mean, a pump dies and it screws up the system, or the power supply dies and it screws up the system. And that's not stuff that you really can deal with. And having to run an experiment that you run for a year before you see any degradation is just very hard to figure out what's going on. And so what we would love to have accelerated degradation methods, but we don't know how to do that. The next thing we really need is reducing the soil voltage. We're running at 3 volts now. That works pretty well. And at today's natural gas prices, because natural gas is really expensive today, it actually works out to be very good. But if you're really running at most, what it was a year ago or 6 months ago, you need to get the voltage down to about 2.5 or 2.25 or 2.5 volts. If you want the carbon monoxide you're producing to be the same cost as the carbon monoxide you do. And so you can run, as you saw, at 2.5 volts, but you need too much iridium in that sense. And so what you need to do is to get more active nanocatalysts for the cathode and for the anode to try to get your voltage down, and also find better conditions to try to run this thing so that you can get the thing to run at these lower conditions. The other big thing is that we need to do something about iridium oxide. When I started this, iridium oxide was perfectly reasonable. It wasn't much. It's about as expensive as platinum. Nothing I really worried about. But now it's jumped 5 times in the last year, and it's very more expensive. So we've gone from about $100 a kilowatt to $500 to $1,000 a kilowatt, and that makes it just too expensive to do that. And so we need to either find some new catalysts, either cause shell structures, or you have iridium, or something we use ruthenium, or some other thing that can last for a long time under our conditions and doesn't need this expensive metal, which is ruthenium. And of course, we have to worry about oxygen removal. If you're trying to run a process and you start off with something that has a lot of oxygen in, and even if it doesn't do anything in the catalyst layer, you're still in trouble because the oxygen, when you put it into your next process, the oxygen blows up when you put it into a high pressure reactor or something like that. So you've got to get rid of the oxygen. Probably you need to just remove all the impurities ahead of time because the downstream processes have a lot of problems with that. Next, I want to mention production of formic acid. That's approaching commercialization at this point. Similar reaction. People also run it with KOH, and at times you make potassium formate, and then you have to revert to potassium formate. And we have to do that. Here's what the 3 electrode cell looks like. Basically, you form formic acid on one cell, you form protons on the other cell, and then they all react in the middle to form a useful product. So again, nanostructures are key. We use bismuth-based things with the metazolium ligands, and that seems to give us the stability, some of the stability we want, and we get high selectivity, as we'll see. DMV uses tin oxide. What happens is they don't have any ligands in it, so they get about half the selectivity, and they need weekly regen. And there's a whole bunch of other things. Indium works, but it doesn't work very long. It has We have all the same problems with the other components. There's 1,000-hour stability. You see that the selectivity varies with the pH because you get the high concentration problem. SOx, NOx, it does nothing. Oxygen, again, is a big problem. There's actually running this in a real power plant, and you can see that it really can run in a power plant. You have a little device here, and it runs perfectly fine on flue gas if you can get the flue gas down here. The neat thing about this is, provided you remove the oxygen, you put an oxygen trap in, and then we can run on real flue gas, and this is real. Stability, again, we have big stability problems. It runs perfect. For some reason, we've run this multiple times, and for the first 1,000 hours, everything runs perfectly fine. And then something goes wrong, and we don't know why. And suddenly the voltage starts shooting up. And it shoots up at like 500 microvolts an hour, half a millivolt an hour, and you need that very much. You also need to suppress hydrogen formation. That runs at higher formic acid concentrations, and we need, obviously, the rest of this is the same. The big thing is you don't want to run with KOH, or if you do, you don't want KOH in your product because then it gets very expensive to separate. There's also a lot of work on Co2 C2 products. I only have to talk about this briefly because I'm running out of time. But basically, instead of being a 2-electron process, this shows that it's 12 electrons, but it's 12 electrons for 2 CO2s, or 6 electrons for each CO. And so you need a lot more electricity to run it, but ethylene is a much more expensive product. So again, people need catalysts, and the catalyst is copper nanoparticles with ligands. A lot of people are using imidazolium-based ligands. We use Sustanium, as does the Bell group. Bell also Prismatium. Sargent group uses a different imidazolium-based ligand on this thing, and Kenneth group and Kenneth Earth group did a different thing. You can also put alloys, and people did that, and that's not very much. I mean, at this point, there's been lots of what I'll call academic examples of actually producing ethylene or ethanol at reasonable rates. Most of the work was done with feeding KOH in the system. Industrially, we never want to do that, but that's what happens, and you get very nice selectivity and activity, and there are multiple examples of that. And so you need to do something about that. You use something with the ligand or the polymer with high pKa. People also looking at a 2-step process, but you don't want to have to feed potassium hydroxide and get credit over your system over the long term. The other thing we need is, so far, lifetimes in my mind have been modest. People have been in 100 or 200 hours. I think there's one case of 1,900 hours. I need, we're running at 10,000 hours, so you just need it to be a lot longer. And another problem that happens is you're making ethanol usually in these things, and it goes over to the anode and burns up again. So you're losing a lot of electrons in that way. And so you have to work out that as well. So in summary, CO2 electrolyzers at lab scale are being widely sold. Industrial scale devices are coming. We need better nano catalysts. They have to be stable for thousands of hours. To do this, they have to have lower potentials, and they have to be tolerant to the impurities, hopefully iridium free. Just a little bit about the oxide materials before I close here. The oxide materials has 2 objectives. One is to develop this technology, and we're trying to do that, create more feedstocks, and we talked about that. But the other thing we try to do is, I'm the next academic, and we want to enable academic and industrial labs to do this. So you can buy all of our state-of-the-art equipment on our website and try to do it. And we're selling membranes, electrodes. We'll be selling these later, just trying to get to larger systems. And I'm completely out of time. Again, this work was supported by the Department of Energy and several contracts, and the U.S. government doesn't make any claims or warranties for what I've said. And there's my contact if you want to see it. And I'll take questions.
Thank you, Rich. Thanks for giving us such a nice introduction from the industrial perspective. I have one question here. So most cases that you introduced start with CO2, right? Pure CO2. But considering the percentage of CO2 in our atmosphere, do you need to integrate a CO2 capture unit with your conversion setup?
It matters what you're starting with. Right now, we're trying to attach our stuff to ethanol fermenters. The trick in a fermenter is, corn is very good at collecting CO2, but the problem is you put it to a fermenter and only half of the carbon ends up in the air. The other half ends up in the product. The other half ends up in your as a CO2 that's emitted. So the idea is to take something like an ethanol plant, which is very good at converting CO2, use the agriculture to collect the CO2, and then use that CO2 that's not converted into products and use that as a feedstock.
Thank you. Thank you for this. And also thank you for contributing the perspective, like CO2 conversion from the industrial perspective to Nature Nanotechnology. It's really nice to have you here. I'm glad that I learned a lot, and I hope our audience also learned a lot from your talk. Thanks.
Well, thank you very much for having me, and I hope that everybody enjoyed the talk. And if you have any questions, just email me. I'd be happy to do it.
Thank
and
you.
I think this talk is going to be on your website somewhere.
Yes, it will be recorded and we will put on the website.
Yeah. Okay. Thank you.
Thank you. Fabio.
Yeah.
Hi there. I was trying to find out what I wanted to share. Sorry, just a second.
Hi Wenjie, hi Fabio.
Hi.
Hello. Hi.
It's very nice to have you, both of you here.
Yeah.
So thanks, Wenjie, and I'd like to thank Rich as well, who's now left us. I just wanted to briefly. So this is Fabio Prizio, by the way. I will just wanted to share you for a moment again what we're doing here. This is a series of webinars that we've organized for our 50th anniversary, and so we've had 7 webinars starting from the 20th of October. The last one will be 1st of December. You can register. It's all free to attend. You can register with a link there. You'll find it on our Twitter, and you'll find it on our webpage as well. So this is our 5th webinar. We'll have one next week and one the week after. Next week, it will be Claire Donnelly and Andreas Heinrich, and they are going to talk about magnetism, spintronics, quantum and quantum nanotechnology, and hopefully you will all attend. You can attend. You can register with the same link as before. I will post it on Twitter, and you should see it also. You should receive an email with the link again. But now I would like to start presenting Professor Yi Cui. I have been practicing pronouncing your name all day, so I hope I pronounced it correctly.
Very well.
And I have to thank Wenjie for this, actually. I'm going to make you presenter. So Yi Cui is a professor at Stanford University. He is a pioneer of using nanotechnology in general, but specifically for energy and for batteries more particularly. So he's published several papers with us. Back in 2007, I believe you published a paper on silicon nanowires for anodes in batteries, and more recently, more recently in 2007, but it was already 2014. We published a paper of Yi Cui on the pomegranate structure for carbon silicon anodes for lithium batteries, and these have been extremely highly cited. And Yi Cui has also gone beyond research and work onto the translation into commercialization of these kind of designs. I believe that you launched a spin-off based on your silicon anodes, silicon nanowires anodes called Empress. Please correct me if I'm wrong.
That's right.
Since last year, you are director of the Precourt Institute, Precourt Energy Institute at Stanford University. So he's looking at energy beyond the work on batteries in a more holistic way. He's looking at energy and sustainability issues with nanotechnology. So I'm really grateful. We're all grateful that you're here to talk to us. I will make you a presenter now, and so you can share your screen.
Okay. Okay, show my screen. Can you all see it?
Yes.
Yeah.
Okay, well, Fabio and Wenjie, thank you for your invitation, and Fabio for the very nice introduction. First of all, congratulations to the editorial team. 15 years Nature Nano. Let me also mention my career growth is together with Nature Nano. I started at Stanford in 2005. And 16 years now. You could imagine my independent research career is really also the process of Nature Nano's growth really nearly perfectly overlap. So congratulations. Now let me share with you, just a second. Let me share with you the topic when Fabio and Alberto asked me to speak. It's on reinventing the battery through nanotechnology. Nanotechnology play very key role right here to enable next generation of battery technology for sustainability. And it's not an overstatement. Nature Nanotechnology, the journal, has been playing a key role and grow this research area, initiating grow this research area, I would say. Well, looking at the batteries application, everybody know electric cars, drone, and stationary energy storage all require energy storage and form very likely all informal batteries, very likely. Certainly long duration on the large energy storage, it might be different solution, but battery will play a very important role. Back in 2019, the Nobel Prize was given to the development of lithium-ion batteries to the three gentlemen based on the intercalation mechanism, graphite, titanium sulfide, lithium coming in and going out, lithium cobalt oxide, lithium iron phosphate, and so on, right? So these materials have very small volume change, but they also have the limit of holding charges. So after this outstanding work, right, of recognized by Nobel Prize, what's really the next? We are asking this question. Grand challenges for the batteries all say, let's reinvent batteries, towards those even higher goals. So first question we ask, how high energy density can batteries go? Measured in watt per kilo or watt per liter, so per weight or per volume. We are now at 250. Can we go to double or triple of the energy density? This has huge meaning for electrical transportation. Can also help reduce the cost significantly because energy density is higher. And can we extend the battery life by 3 times or more? Cycle life, right? Let's go to 10,000, 30,000 cycles. Calendar life, instead of 10 years, can we go to 30 years? So then your batteries used in electrical car, once they are retired, they could be used for grid scale energy storage. For the electrical grid, you really want your batteries 25 years, 30 years or longer life. So currently, we cannot do it. How fast can you charge out your batteries? Can you do it within 10 minutes without sacrificing your performance in terms of energy density and lifetime, I don't think we are there yet. So this has huge meaning for large scale deployment of electric car, deep penetration of electric cars. Can we make batteries completely safe without accident, without catching fire explosion? You have seen these fire accidents just keeps coming, no matter it's portable electronics, electric cars, large scale energy storage news. Once in a while, you're going to see it. Once we have a deep deployment of electric cars and large scale energy storage, this can become sometimes a disaster situation. Can we make them completely safe? What about the cost? We want to reduce the cost by 3 times or more, particularly for long duration storage like seasonal storage. We want it to be 10 times low cost of the current technology. How do we sense the interior battery health condition? And what about the battery reuse and recycling? And grid scale and seasonal storage, flexible, variable, stretchable applications, right? These really present new opportunities for the batteries research. These are the questions the existing batteries cannot answer. This is also where the nanotechnology can come in, can play a very important role. So over the past 15 years, my lab has been developing research programs to answer some of those important questions. Let me today, for the purpose of celebrating Nature Nanotech's 15 years, to give you only some selected examples I see could be very important for the whole community to look at and really think deeply, what's next we should be doing. So talking about high energy density, this is the plot. Vertical axis is the relative volume change. Horizontal axis is the ratio of lithium versus the host atoms. Current technology really only explore the ratio about 1 versus 6. And the volume change is less than 10%. But to store a lot more electrons, you need to store a lot more lithium. Lithium has its volume in there. And with oxidation state change of your host materials, there will be very big volume change associated with new materials going up all the way to metallic lithium. And the relative volume change is actually infinite. This is the plot my postdoc Yayuan Liu made. She's come to MIT. My graduate student now postdoc at MIT. She's joining Johns Hopkins as a faculty starting January. So in the new material, you store a lot more charges. You are going to have significant chemical bond breaking, host atoms to move to long distance, complete structure change, huge volume expansion, and this really require you to design the materials in a very different way. So using nanotechnology can be crucial to solve this problem on the right-hand side with very large capacity. Right, these designing in the nanoscale, enabling the electrode scale and the whole battery level of design will be very, very important. So if you are able to do this successfully, you can move from graphite MMC combination, the current technology, roughly 250 watt per kilo, to silicon MMC, 400, lithium metal, 500, and or if something like lithium sulfur, 600, 700, or maybe even 800. So we are talking about doubling or tripling of the energy density per unit weight of the batteries. The impact is just gigantic. So what are the key problems right there? Back to the first very exciting example in the early days, Fabio referred to is the silicon. Silicon store 11 times higher capacity compared to graphite carbon, right? 4,200 milliamp per gram. But silicon has this huge volume expansion problem and then associated mechanical breaking. Once you break the materials, you lose electrical contact. You expose large surface area to create more side chemical reactions. So how do you avoid breaking? And how do you build stable solid electrolyte interface? These two questions are very, very important to answer. Well, back in 2007, actually the paper came out in 2007, the formal issues of January 2008. We demonstrated the first example of rational design using nanoscience concept to develop silicon nanowire anode and electrically connected with current collector, right, by grow directly silicon nanowire from a stainless steel current collector, maintain electron transport, and the diameters are small enough. You can do the very good strain relaxation without breaking. So you maintain this contact back and forth. You can do lithium ion charging in and going out reversibly. This was my first graduate student, Candice Chen, a faculty member at Arizona State, right, working on this project. This turned out to be the paper. And now I just look at the citation, it's more than 6,400 times. And really, this is I will consider as a landmark paper to initiate the nanoscience approach for the battery design and in a rational way. So, and with this nanostructure, with the new tool development, for example, in situ transmission electron microscopy, this is in collaboration with my colleague Bill Nix, a mechanical expert, and my early graduate student Matt, spending a lot of time working on it, and now a faculty member at Georgia Tech. And with this in situ TEM holder, and you can mount a nanostructure such as nanowire to a GoPro and poke it into ionic liquid electrolyte. The vapor pressure is low, so it can survive in a high vacuum condition. You have a counter electrode supply lithium, that's lithium cobalt oxide, apply a voltage, and you can drive electrons coming in, lithium diffuse in, react with silicon, looking at the lithium silicon reaction in operando inside electron microscope. Using this platform, we can also put the particle stick to wires, and lithium can also diffuse into the particle and neutralize with the electrons. This is one of the in situ video already speed up multiple times with 200 nanometer scale bar right here. This is about 200 nanometer diameter silicon nanowire surface coated with copper. Lithium coming in, the volume expansion is a lot. And this volume expansion is so powerful, break the copper coating on the surface. But silicon nanowires do not break. That's very important. So the next video I'm going to show you is the case. Once you have a particle, the size is big, in the center right here, 800 nanometer in diameters, compared to the small particle in surrounding, we try to answer the question, what are the critical breaking sizes for the particles in the nanowires? Below those sizes, they do not break that easily. What you are seeing right here, lithium coming in, made the silicon particle volume expansion taking place and create this lithium silicon alloy on the shell. And this big particle accumulates so much stress and strain, and it cannot take it anymore. It's broken. Using a tool like this, our critical breaking size identified is about 150 nanometer for nanoparticles, close to 300 nanometer for the nanowires. This detailed chemomechanical reason behind it. I will not have time to go through that. But what's really exciting right here, we identify the critical breaking size as a material design principle, the guideline for the whole industry to follow. If you do not want to have the breaking of the nanostructure, what will be the sizes you are looking for? So we passed about 15 years of research. And my lab starting from silicon nanowire and really demonstrate a number of material design concepts with a deeper nanoscience design behind it. And try this design would help to overcome the problems of breaking, forming a stable interface, and how do you minimize the surface area of nanostructure to avoid more side chemical reaction. So let me highlight a few right here. And I believe with all this generation of design, we are already figure out all the material design principle to help industry to move forward towards a larger scale deployment commercialization. So let me highlight, this is also very important for thinking in the design is how do you build stable SEI, the interfacial structure? if you take a nanoparticle or wires, the solid one, you put lithium in, their volume will be expanded. And then you take lithium out and shrink, this interfacial layer, decomposition compound called SCI will be broken. So before long, you're going to build a really thick SCI. You consume too much electrolyte, your battery will die also. So how do we solve this problem? Hui Wu was my postdoc at the time, and now a faculty member in Tsinghua University. And we say, well, what about hollow structure? Well, hollow structure also volume expand towards outside. And then once you put lithium in, you take lithium out, they shrink. It's similar. What do we really need is this concept breakthrough is the double wall hollow structure with silicon, the blue color inside. The red color is silicon oxide, for example, is mechanically strong. Once lithium coming in, force the silicon volume expansion towards inside. And once you take lithium out, the interior surface moving back, but the outer surface never move. This is really a big concept breakthrough. And in this Nature Nanotech paper, we show this. This has been providing the guiding design principle for the whole research community to use is how do you build stable interface? It doesn't need to be these double wall hollow tube. It can be other structure, but the concept is there. So I want to highlight the citation of this paper. This reason why the citation is so high, because this concept really solve one of the really challenging problem in the battery field is with high capacity materials, you have to have volume expansion. But if you have volume expansion towards outside, you are not going to be able to build a stable solid electrolyte interface. Now create interior empty space, let the volume expansion go towards inside. This really solve the problem. You keep the outside interface never moving. So we in this paper, we demonstrate double wall hollow structure after 2000 cycles, right? The SCI on the surface of this hollow tube is still really, really thin for the solid wire and single wall hollow silicon tube. And after 200 cycles, you just have so much SCI built up already. So these are all very exciting. But it's one big problem for the nanostructure in the battery field. Everybody by now already know about this. Is too high surface area is not good. Nanostructure will have a very high surface to volume ratio. Then you have a lot of surface to decompose the electrolyte and for the anode side. So your Coulombic efficiency will be really, really bad. So how do we solve this problem? And also there's another problem is nanostructure, its tap density is low, its volumetric capacity can get damaged. But if you look into this issue further, no, that does not need to be the case. We could solve this problem by a materials design. This is what Fabio referred back to the 2014, this paper in Nature Nano, the cover paper. And we pack the silicon nanoparticle into secondary structure, forming this permanganate-like structure. And then we coat the outer surface with carbon, and you seal the secondary structure with carbon. So each of these nanoparticles, you don't want each of them to expose to the electrolyte. You want the secondary particle surface area exposed to the electrolyte. Reduce the surface area, and then you can link the structure together in a very dense way. You increase the dense packing, and this helps you to increase the mass loading per area because you already use carbon to link all these materials together. So through this design, roughly you're packing about 100,000 of these nanoparticles into a secondary particle, right? Get to about 5-6 micron secondary particle range. This provides you a new design that solve the problem. It's really one stone and hitting multiple birds, solving all these three problems right there. We develop a really cool synthesis method to make this structure, and demonstrating this concept is really working very well. So with all of this, back in 2008, I co-founded Empress, and to commercialize our nanostructure silicon technology. And Fabio and Wenjie, this is very exciting. Right? Empress has a 450 watt per kilogram of battery supplied to Airbus and also other companies. This is the highest energy density batteries, rechargeable batteries in the world, really working well. Empress in the process to do scale up production of this nanostructure. There's also silicon nanoparticle solutions, in amperes, based on some of the concept design in my lab, and that can offer 330, 350 watt per kilogram of the batteries that could have already available and low cost, supplying to many battery manufacturing companies. So silicon, I consider these 10 years, right? This decade is the golden time for commercialization of silicon. Everybody, you're going to see industry really know now how to use silicon better and better. This will go into commercial space more and more. So let me highlight these tales of invention one-pager article I wrote, and to tell people about the story of silicon anode from beginning, starting from the 1970s, 60s, 70s, when people recognized the lithium and silicon can alloy, and until now. What's the story about silicon, right? What's the story really behind the invention? So why the nanoscience approach back in 2008, 2007, our nanowire papers is so important as a milestone to encourage the whole research field to use nanoscience design in a rational way to enable new type of high capacity materials. So then what about next? So what's after silicon? Assuming we can, in this decade, we can make silicon to work, right? What can go beyond the current decade? So we need to revisit lithium metal anode. This is the holy grail of batteries. Lithium metal anode has no host. And if, for example, you take a lithium metal foil, put it into the electrolyte, and you're going to form the SEI structure. If you play lithium, and lithium plating, there's no guarantee it's a flat layer by layer. You're going to cause surface curvature change, and you're going to break this SEI. This is the hot spot right there. You expose fresh lithium surface to the electrolyte. Lithium flux will go to this hot spot and grow out this lithium filamental structure. And once you strip lithium away, you probably easily will strip from the bottom, not only from the top. Then you cause this isolated lithium to become a problem. Oftentimes people call this as a dead lithium. You lose this lithium, right? And then your capacity will decay really fast because of this dead lithium. It's also because every cycle you need to reform the solid electrolyte interface. And during this process, and you need 3 milliamp hour per centimeter square of capacity. Sometimes you even need 5. So 1 milliamp hour is 5 micron. 3 milliamp hour will be 15 micron. Every time you do plating, you plate 15 micron. When you do stripping during discharge, you strip away 15 micron. Each layer, the volume change is so big. You cannot handle this. And this is the perspective we want to share with whole community. I still remember back in 2016-17 timeframe, I was talking to Alberto, the editor in Nature Nano, right, and saying, well, nanoscience approach could play very important role right here. So this is the perspective article we wrote, with actually very high citation, 2,900 times more than that right now. This has been sharing with the whole community. What are the root causes of the problem? The root causes are high chemical reactivity of lithium and this relative infinite volume change of this lithium. You lose control because when you do plating, lithium fills up. When you do stripping, lithium becomes empty. The volume change in a relative sense is infinite. This causes all the surrounding problem, no matter it's dendrite formation, internal shorting, low Coulombic efficiency, SEI buildup. These are the surrounding problem. In order to solve the root causes, we need to come up with a strategy for overcoming those problems. So, and at Stanford University, when Steve chose, after he stepped down from Secretary of Energy position, coming back to Stanford, he and I have been collaborating. Particularly, I want to highlight, we come up the first concept of stable host design. And lithium metal host, lithium metal doesn't have a host. We need to build a host to contain its volume. If you don't contain its volume, it will be very challenging to build, a stable interface. And for stable interface, we need to come up new strategy. It needs to be chemically stable, mechanically resilient. Which about over the years, we have been coming up a number of ideas to solve this problem, particularly using a new type of polymer approach and also new type of electrolyte. So let me highlight some of the advancement in these areas. One big advancement is how do you host lithium metal, learning from lithium ion stored in graphite, lithium ion stored in silicon. Can we do this for lithium, that's metallic lithium, and contain in a host? So we designed this hollow carbon structure with a seed in there to help promote the nucleation of metallic lithium inside instead of going outside. We discover for different materials, lithium metal deposition have a different over potential. For metal like gold, nanoparticles in there's no nucleation barrier. On carbon, there's some nucleation barrier right there. So during deposition within certain current density, we could expect lithium metal would deposit inside instead of going outside. Then this stable carbon can function as a very good interfacial structures to stabilize the lithium metal. So we went ahead and made this structure. And this is a TM image. This particle roughly about a micron or less, right? This hollow particle with the nanoparticle decorated inside. You can control the number of gold nanoparticles and to control how many nucleation sites you could have. So using a tool like in situ TM to deposit lithium metal into this host, you can see lithium coming in can dissolve gold nanoparticles away. Lithium really have good affinity with gold. That's the reason gold can function as nucleation seed. And once you strip lithium away, we are going to see this gold nanoparticle will precipitate back. And this gold has solubility in lithium is very important materials guiding principle, not only gold, zinc, magnesium, silver, and this can all work. So this open up the low cost materials for nucleation seed. So using these seeded hollow carbon in figure B, and once you build up the battery electrode, you deposit lithium. Now you see after deposition, you don't see lithium deposit outside. If you only have hollow carbon, you're going to have this lithium metal nucleation and growing, forming this filament outside. So figure A, this hollow carbon alone will not be stable as the electrode, but B will be a lot more stable. You know, our experimental data has been showing this. Now the question becomes to really build up the a whole structure in a realistic sense. What will be the ideal host that can be processable, low cost, that can be very effective? And Ding Chang and Yao Yuan are the two graduate students. They were now postdoc at two different places. Actually, both of them will be joining Johns Hopkins as faculty next year. And they were the people working on this problem in my lab. And this also becomes a very important milestone in the field of this graphene oxide host we come up in this Nature Nano paper. Before graphene oxide, we indeed try a number of other carbon hosts because carbon is lightweight. You do want to have a lightweight host, right? No matter it's nanotube film, carbon fiber, and you melt this lithium metal, the melting point is low, right? We develop a molten infusion process. However, they don't like to wet. You see this lithium metal, a molten liquid, they bore up. But until we try graphene oxide, now we see lithium metal wet and goes in. Apparently, there's a wetting phenomenon going on right there. So we call a new term mimicking hydrophobic hydrophilic. For the wetting case for lithium, we call it lithophilic. The opposite will be lithophobic. This turned out to be the term after this 2016 paper now is now widely used in the battery field. Lithophilic, lithophobic, and other groups mimicking this and say for sodium case will be sodiophilic, sodiophobic. For potassium's case, so you can do the similar, terminology right here. So this very lightweight reduced graphene oxide, after you put in molten lithium, there's a spark reaction, opening up the gap. graphene oxide has the OH and COOH on the surface that's polar, that react with lithium metal a little bit with the delta G that gives free energy of reaction to be negative. So the surface of graphene oxide is wetting. This nanoscale gap offer a capillary force to really pulling in molten lithium into the graphene oxide and now host it between graphene oxide. Now graphene oxide can maintain the volume of this lithium metal during stripping and plating of a whole structure to have lithium metal deposition to minimize the volume change. So we show in this paper, it's actually working very well, this concept. So with all this development, we do have a question we keep asking. So how do we figure out the atomic scale level structure for battery material that are fragile like lithium metal, like a solid electrolyte interface, right? And for example, this is room temperature TEM. If you zoom in of lithium metal, you are going to destroy these materials. And lithium's melting point is very low, 190 degrees Celsius roughly. So they're not stable under the beam. So I've been working on battery for so many years, I haven't seen atomic scale resolution of metallic lithium yet. I have not seen atomic scale resolution of solid electrolyte interface. So, but we do need to understand these materials. How do we do that? So in 2017, we published this paper in Science, and we borrow from structural biology and utilize that, develop it further for battery material, cryogenic electron microscopy. We deposit lithium metal onto the TEM grid, develop a very important thing is a cryo quenching, punch freeze, how do you freeze the sample? How to develop the cryo transfer to go into DTEM without exposed to air, yet maintaining liquid nitrogen temperature. Yu Zhang and Yanbing has been doing that. Yu Zhang just joining UCLA faculty last year. And for the first time, we were able to resolve atomic scale resolution of metallic lithium and really understand its growth habit, its dendrite growth, what's the crystallography orientation, what's the sidewall facet. So this is the first time we could understand this question. Not only that, this is also the first time we can resolve SEI structure. This is a lithium metal, and now the SEI clearly seen in this FEC, ECDEC with FEC as the additive. This is a fluorinated ethylene carbonate electrolyte, right? You have about 20 nanometer thickness with amorphous layer right here. On the top, this is this inorganic layer, very uniform lithium oxide layer. And we resolve the SEI structure. And once you change the electrolyte, it can present to you a different structure, so-called the mosaic pattern we observe in the science paper. For the first time, we address the long outstanding dispute about what's the SEI structure, whether it's mosaic or multi-layer, how do they look like? So we offer the first lattice resolve evidence of the SEI structure. Let me emphasize, in the past roughly 4 years, and cryo-EM has been shown to be a very powerful technique, starting from our first demonstration and the science paper. Now, just for my group, we have a number of demonstrations, many observations for the first time. Very important discoveries right here. And we will be having another paper coming out soon in Science to describe the SEI with solvent swell inside. There's a dry state and wet state. There's a very dramatic difference right there, providing the guideline what a good SEI should look like, how much swelling effect it should be have. So stay tuned. Let me also emphasize a lot of these ideas. We have this perspective article in ACS Nano about the opportunity of cryo-EM for material science and nanoscience. I would like to bring to your attention. And also recently, I serve as a guest editor with Lena and Cornell University, and having a theme issue of account of chemical research on the cryo-EM. A lot of good ideas right there. What cryo-EM can do for for sensitive materials, for quantum materials, for biomaterials. go read about this theme issue. There's multiple excellent articles right there. So at last, let me try to address one of the questions, and very important. With the batteries coming up more and more, right? With the electric cars, we have 1 billion passenger cars running with 350 million buses and trucks. So to decarbonize this area, to make it electrical, we need a lot of lithium-ion batteries. We need a lot of lithiums. We need a lot of resources. We need nickel, we need cobalt. How do we get the resources? And for about close to a decade now, my lab has been trying to do is to extract valuable resources from nature, for example, from brine. So particularly for lithium, I want to highlight this one example. Steve Chu and I work on this together with our joint postdoc, Chong Liu. Chong now is a faculty at University of Chicago, is to come up method to extract lithium out of a non-traditional lithium sources. For example, seawater. For example, low concentration, 100 ppm or lower of those brine. But what we need is a technology that can have very high selectivity of lithium versus sodium, lithium versus magnesium. Leveraging what's been developed in the battery field, for example, lithium iron phosphate is a materials you could recognize lithium more than sodium within certain potential range with very high selectivity in the order of 10,000 times. And this provides the opportunity, if you do the battery charging, you can put electrons into lithium iron phosphate, get the lithium coming in instead of sodium. Now you can extract the lithium with such high selectivity, make it possible. For example, right here, this is the Salt Lake in Utah, right? It's like really close to Salt Lake with about 20 ppm of lithium. With one-step extraction, we can go up to more than 90% of purity right there. With seawater, lithium versus sodium concentration, lithium is to sodium is 10 to minus 5. With that, even with one-step extraction, we can concentrate lithium to 50% of purity in the seawater. So this type of approach, it will offer ideas. How do we come up much better extraction, separation, purification technology down the road using nanotechnology, and particularly will be able to help. So this could be a great opportunity as a very exciting areas of resources extraction. I think Wenjie and Fabio, I probably have a few minutes. Let me share with you what Fabio mentioned, and it's also the important time for sustainability to translate the science and technology into the real world. In the past, I've been working on amperes. I started amperes back in 2008. And 5 years ago, 6 years ago, as Steve Chu and I started 4C Air using nanofiber technology to filter out particles, viruses. Turned out to be during COVID-19. We were able to generate the best facial mask and the N95 level in the world with amazing breathability. And I set up a technology accelerator, taking multiple technology developed from my lab into market. We recently spin out grid-scale energy storage company in Vanille, based on a paper we published on the nickel hydrogen gas batteries, manganese hydrogen gas batteries. We also work on the cooling and warming textile, recently spinning out Life Labs. This technology really based on the nanotechnology, control human body infrared radiation, having the best warming and the best cooling clothing in the market. These will help saving building energy consumption, having a low environmental footprint, this fabric, right, to enable sustainability. There will be water technology coming in, soil cleanup, and green building material. I won't go into the details. So at last, let me share with you from the perspective of a Precourt Institute. Starting from January, I took on a director position. We are really positioned ourselves at Stanford right here to help to enable sustainable, affordable, secure energy for all. and built on the previous 3 directors. And we now have an amazing institute and academia to help the world to realize this vision. And given the current commitment from multiple countries, from also Fortune 500 company, more than 60% with climate goal, Amazon's climate pledge by 2040, right, carbon neutral, more than 200 companies joining in. I want to share with you, Stanford is starting a new school focused on climate and sustainability. We announced that last year. The blueprint come out this year. The official starting date is the next fall. And we are now really preparing the whole Stanford energy community to respond to this great opportunity. Stanford has been having an amazing number of faculty, 200 plus and more, and 1,000 plus graduate students and postdocs. With previous highly powerful people, the former cabinet member and US government, as a faculty here to work on energy problem with a lot of science, engineering, technology expert. We really do have from science, engineering, technology to economics to policy and to work on energy problem. So, and how do we decarbonize the economy, right? Really need to look into, well, where the CO2 really coming from. Electricity sector, that's great. Transportation industry, commercial residential building, and agriculture. At Stanford, we have multiple initiatives to help addressing this problem. For example, bits and watts, that's a smart grid to help decarbonize the grid. And Storage X, our Storage X initiative, the batteries for electric car, the long duration storage, natural gas initiative, how do you utilize natural gas without emitting CO2? We have Catalyst Center, Material Center funded by Department of Energy. We are in the process of starting our carbon removal, hydrogen, and sustainable manufacturing initiative. What's also very important is sustainable finance. We have sustainable finance initiative to look at this problem, policy, education, external communication, using big data and AI to plan for the future energy system. With our new school coming in, we'll be doing a lot of technology translation. You all know Stanford is famous for spinning out Silicon Valley. So we hope Stanford will play a very important role to help spinning out an energy valley right here in Silicon Valley, and the social human behavior and global engagement. So, and I probably need to just end my talk with this last slide. Stanford is having a blueprint, starting this new school. There will be roughly close to 10 new departments coming up, and our institute will be cross-cutting the school and the whole university, and together with our Woods Institute for Environment, and we will have an Institute for Sustainable Society to be set up. There's a sustainability accelerator under planning right now. These are all very, very exciting. With that, I'm going to stop right here. I will be happy to answer any questions you have.
Hi, and thanks a lot for this. It's really incredible talk. Thank you. And you went through a lot of stuff, and all very interesting. Yeah, you can leave this on actually if you want to. This last slide is very interesting. Just a quick reminder to the attendees that you can ask questions by putting them in the question box, and I will then ask them to you each way. Let me just. I have a very general question. I was really intrigued by your slide about the recovery of lithium, right? And from seawater. We had Menachem Elimelech 2 weeks ago, who was talking about iron selectivity. And so that's a very important issue, recovery of not just lithium, but in general phosphate and other elements from the environment. Conversely, what about recycling batteries? I mean, is there any? This is a very generic question, but is there any specific difference into having nanostructured batteries towards recyclability? Because that is one of the problems with batteries, right? So it's like with any other energy device.
Yeah, Fabio, you're asking a very important questions. This lithium extraction, nickel, cobalt, and others. Just in general, I think it's worth to look at how do we extract stuff out of the earth using probably developing a new process in a more sustainable way, use less acid, right? Use less energy and use less water. And then coming back to the recycling part has been, using the traditional technology for doing it. I think there's an opportunity to relook at the recycling. How do we do that? And then using the nanostructure batteries, whether that made the recycling easier. Well, I don't necessarily think it made the recycling easier. That's probably not the impact of using nanostructure inside the battery that can enable. But I hope we could, based on this process happening in nanostructure, this can give us more ideas of how do we do extraction more effectively.
Thanks. Okay, there is another general question from the audience. So have you got any idea of what is the future of sodium-ion batteries?
Yeah, so the sodium coming in, the value is really try to say, hey, if we don't have enough lithium, we need to explore sodium as one of the biggest value proposition. The second one will be because the sodium behavior is different from lithium. Maybe some of the host materials, lithium coming in and going out, and compared to sodium, the performance is not as good. Sodium can enable those materials. So for that one, for few materials, I get it. And for the case of lithium and sodium, the resources availability, my personal thought is, no, we are not running out of lithium. We have a lot of lithium. There's a lot of resources right there for lithium to go to the scale we want. However, I don't mean we shouldn't do sodium ion research. And in everything, you need to have insurance policy right there. And even we have enough lithium, but lithium price fluctuation is enough to also cause fluctuation of the batteries, right? Having some fundamental and applied research on sodium has a lot of great value right there. But I need to be honest to the audience, everybody needs to be honest, we are not really running out of lithium.
Especially if we can recover it.
That's right. We can reuse it, recycle it. Yes, that's right. Yes.
Well, it's another another question. So the question is there any chance of using the nanostructure batteries in powering cars? And I guess I would extend it to, so how far are we? I mean, hopefully, I would say I can answer the question saying that hopefully yes, there is, but how far are we to commercialization? I mean, you yourself have said, this is the decade for commercializing silicon in energy, but what is how far are we from commercializing nano batteries? It's not nano batteries, but nanostructure batteries, if you see.
Well, it's already some of this nanostructure battery already used in commercialization, consumer electronics, drone, and some of them already start to get into the car. Well, if you look at Tesla's announcement, right, of using silicon, one type of silicon, whether how nano that is, I don't know, but those nano design concept got to come in. And Amprius is doing that. Amprius now try to ramp up the production of both the silicon nanoparticle graphite mixture as well as silicon wires. So you'll be able to see this will start to get into a car in the next couple of years.
Good. Well, thank you very much. I will let you go. I know you have a very busy schedule. I'd like to thank you again for being with us today, and thanks for your contribution during the last 15 years, indeed, and thanks for your time today. And with this, I'd like to thank also the audience. This is all we have time for today, and I hope you will join us next week again. And for the time being, thank you and goodbye.
Thanks, thank you, Fabio. Okay, thank you. Congratulations.
Thank you.
Okay, bye now. Bye,
Bye-bye.
everybody.
Bye.